Hello everyone, I'm back with a new project about integrating experimental data into Abaqus UMAT, a comprehensive approach from testing to model calibration. In this tutorial, I'm going to explain how to find your material property and define in your Abaqus CAE or in your UMAT subroutine. And then calibrate your model with a single element, and then use calibrated model, calibrated property in your real model or real project. So before starting this tutorial, please subscribe my channel to get lots of information about FEM simulation, machine learning, writing a script and other thing. And by subscribing my channel, you can increase my motivation to prepare more practical project and tutorial for you. So uh, as I told already, I'm going to explain a step by step to prepare your tensile test model, which kind of test you need to do, and then find your material property, I mean extract your material property and then use in your CA model, and finally calibrate your model. First of all, it's necessary to prepare your tensile test specimen. In this project we use polymers, so it's necessary to use ASTM, we use ASTM D638 standard to prepare our specimen. As you know, for different material, you maybe use different or various STM model or other standards. So it depends on your materials, metal, polymer and other things. After that, for this project we use tensile test and also loading and unloading test. First of all, we prepare the tensile test specimen and install in tensile test machine and do tensile test. After that, we use raw data to prepare our true strain, plastic true strain and true stress, plastic strain and stress. After that, we also perform a loading and unloading test, and then we use raw data to prepare through a string to assess loading and unloading assess. After that, using these two uh, test, we prepare our material property. In this model we use a short model to calibrate our model in a single element using Abaqus CAE model. So as you can see here, this is our loading and unloading, so it's necessary for us to calibrate this material behavior in our model, and then use this subroutine, UMAT subroutine, in our real project. We use short model. First of all, we define initial elastic model and position ratio. We use this data from our experimental test, tensile test, and also we find a young yielding point using tensile test. After preparing the material property related to tensile test, we need to find our elastic modulus using in short model. As you know, our elastic modulus during loading and unloading decreases, so it's necessary to find the Young's modulus using short model. So as you know, short model use this equation and they use 2 point from from each loading and unloading cycle. So we choose 2 point, for example, for the first loading and unloading, for example this point and this point. For example, this point is sigma 2 and this point is sigma 1, sigma 1 epsilon 1, and sigma 2 sigma 2 epsilon epsilon 2. So using this equation we define this point. As you know, the first point is our initial elastic modulus, so we define here and then for the defining this point, it's necessary we consider this point and this point, sigma 2 epsilon 2 and sigma 1 epsilon 1, and finding this point. And for this point, it's necessary to consider this cycle or the second loading unloading cycle. So we consider this point and this point, and for this point as a last point in this graph, we consider this point and this point. It's necessary to explain in short model which we use in this project. We didn't consider this distance during loading and unloading. If you want to consider this distance or gap between loading and unloading, it's necessary to use, for example, quasi-plastic model. And so in quasi-plastic model you need to define more or extract more parameter and define in your UMAT subroutine. So after preparing this point from your loading and unloading, you need to define or calibrate your short model using CAE model. So in your CAE model, we define initial elastic modulus and position ratio, and then define 5 dip var S0 Q curve, and also final Young's modulus and eta as a decrease of elastic modulus during the loading and unloading. You can see this is our calibrated model from CAE model, and then we use this calibrate data in our real project. And so so I will explain how to calibrate, how to define your model and find the calibrated data. Before showing the CA model, I need to explain for the elastic or hardening elastic plastic model or hardening model. We use which type. You can search about which type and get lots of information from Google. We use define stress and SU initial stress Q as a isotropic hardening model, and K is a and also isotropic hardening model, and then epsilon P or plastic strain. For finding this equation, we define three parameter, and for the short function, as I explained already, we define initial Young's elastic modulus E0, and also find the final elastic modulus means that this one, from the last cycle. We consider this one, I consider this one because this is the value of the last cycle. And another one, we need to define rate of elastic modulus in short model means eta. And I mean calibrate this model or find this model to calibrate our material behavior. In your Abaqus model, you need to define uh, cube as a single element. Cube single element, we consider 1 millimeter, 1 millimeter, and 1 millimeter as a dimension of this cube. After the drawing or defining your model, it's necessary to define your material properties. So as I explained in the last slide, this slide, you need to define your material property as a depth var. So it's necessary to go general, tab, and define and click depth var, and define your number of solution depend. As I explained, we need to define 5 solution depend, and also after that you define your after defining your depth var, you need to select a user material. So you need to click general and define your and click a user material and define your depth var. This is the calibrated data, but when you start this kind of simulation, you don't know about this one, and this one. You need initial elastic modulus, Poisson ratio, Young yielding point, but you don't know isotropic parameter, this one and this one, and also you don't know the rate of the rate of elastic modulus, decrease of elastic modulus. So you need to calibrate or finding this 3 parameter. After that, after defining your material property as a data, you need to define your step. We define a step static general, and time we consider 11 second as a time period, and LGM we consider on because we consider large plastic deformation, and also after defining this one, you need to constrain your model or your cube based on this figure. We As you can see here, we define displacement in u1 0.01, and define amplitude. You can see the amplitude from 0 to 11 second, and this is the amplitude value from during this determine time. After that, we need to constrain this direction x x symmetric, and define this section as a z symmetric, and this section as a y symmetric. So we can see the x symmetric, y symmetric, and z symmetric for this cube. After that, as I told already, we need define one or single element for our cube, so we can see the global size 1 millimeter. After that, you need to define your element type based on this window. And finally, we after finishing our simulation, uh, I will show you in this video. Okay, in this video I will show the simulation. You can see 11 second loading, unloading, loading, and unloading. So okay, and we define 5 state variable or depth bar as our isometric parameter, and a short model. After that, I will show you how to extract your strain and stress curve, loading and unloading curve. So it's necessary to go create XY data and create ODB file output. After that, select your LE in one direction, and stress in one direction, your loading and unloading direction. So click this one and plot this two figure. It's necessary also to go in element node tab and select your select element set. After that, plot these two figure. You can see this one is stress are S11, and this one are strain LE 11. After that, it's necessary to combine these two figure to see we manage to calibrate our model or not. So we use operate on XY data and choose combine tab and select these two plot. As you can see in here, this is our loading and unloading data from short model. And if you want to consider other model, as I explained already, consider plastic QP model and define or consider this distance, and calibrate your model more accurately. Uh, more accurately. Okay, thank you for watching this video. I hope you enjoyed this video. If you subscribe my channel, you will support us and also increase our motivation to prepare more practical video. Good luck. See you soon. Bye.